Okay, let's continue on here to chapter 4, discrete random variables. This is going to look at where probability blurs with statistics, and it's really going to tie in a lot of the things that we've already talked about thus far. The first thing we're going to talk about is probability distribution functions for discrete random variable. So random variable describes the outcome of a statistical experiment in words. It says words. I would think of it as a number, though. A random variable is a number. It's the outcome of an experiment put into a number. So consider an experiment where we're going to flip a coin 4 times. The random variable will be determined by that experiment. We're going to call that random variable x, the number of heads in those 4 flips. Possible values of x are x equals 0, 1, 2, 3, or 4. You're going to flip it 4 times. Any of those are possible. That then becomes your random variable, the outcome. Now, if I was to stay on this for a minute, flip a coin 4 times, and that's my experiment, and I decide to replicate it over and over and over. Well, what do we think that shape would look like by the end? We know that it's really common that you're going to have a head. It's possible that you might not have any head. Also possible that you might not have any tails. So, you're going to end up with something that's a bell shape, right? It's going to look something like this. That's going to be empirical. It's going to come from the actual experiment itself. But you could also think of that as probability, right? You're going to start at the left, and I know what the odds are of having 1 head, and 0 heads, and 2 heads, and 3 heads, and I know all those because we know how to do probability at this point. And once you do that experiment infinite times, because of the law of large numbers, you know that you're going to end up with a shape like this that is true to the correct probability over here. Now, let's go to this example. Sorry, these were not the same values shown on here. There's more outcomes, just talking about the shape for that heads and tails example. But let's talk about a discrete probability distribution function with 2 characteristics. So each probability is between 0 and 1, includes 0 and 1, and the sum of all the probabilities is equal to 1. So as we see here, 4 over 50 plus, add all these up, you're going to get 50 over 50. Now, this is a chart that's going to be super helpful with this, and we're going to translate this chart into a histogram and kind of describe how we get to a distribution. So researcher, this chart is given from this information here, which is a researcher is on a 12-hour shift. They want to see how many times a patient rings for the nurse. So X is the number of times that a patient is rung every single night, or a nurse is rung from a patient every night. And it goes between 0 and 5, and it's always one of those. It can't be a half a time. It can't be more than 5. So that's just how it's given. And then we have a probability. This one was done empirically, right? Because there's no correct true odds on this. But similar to how if you flip a coin enough times, you get an idea over what the odds are if this was taken. So this distribution here was taken over 50 patients, and they start to get a little bit of a sense of the probabilities. So here's our probabilities. Now let's go ahead and look at what it looks like in a distribution form. You can see it's normally distributed. And that sets the ground for our probability distribution function. Now, think about this is discrete, right? You have to have a true 0, 1, 2, 3, 4, 5. Now, if you made these bins really small and kept making them infinitely small, and you can be any number in between 0 and 1, then we start to end up with a line, and that gives us a true distribution, probability distribution function. So I've talked a little bit about what we expect to happen, right, and the law of large numbers. This is where that really comes into play. So first of all, we have, for the above example, we have a probability that we have 0. We have a probability that we have 1. We have a probability that we have 2. And we know these probabilities. We also know the value of our random variable here, which is on the x-axis 0, 1, 2, 3, 4, or 5. Now, what do we think is the most... What do we expect that random variable to be? So we have 50 patients. We have an idea of what to expect. Now we grab one at random. What do we think that their number of rings is going to be in a night? Well, looking at this, this is after looking at all 50. We want to just look at one person. Where do we think that they will lie? Most often, they will be somewhere in here, right? We expect them to be towards the middle. It's possible that they're over here. It's possible they're over here, but we expect them to be somewhere there. So let's talk about expectations. The expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment, you would expect this on average. So it's possible one person that we draw might be towards the end, but if you were to take a gamble and have to predict where we think somebody's going to be, we're going to expect them to be towards the middle, right? That's what the law of large numbers is telling us. Let's walk through a quick example. So, our random variable here is x. We have possible outcomes 0, 1, and 2, and the probability of those outcomes, 0.2, 0.5, and 0.3. Our expectation, our expected value, is calculated by x times probability of x. So, how often do we end up with 0.2% or 20% of the time, right? We end up with 0. Then we're going to look at the expectation of ending up in 1. That's going to be 0.5. And the same for 2, 0.6. Now we add all those values up and we have the true expectation of this distribution. So given all the information we know, given the PDF, given the table, we end up with a mu equal to 1.1. The expected value is equal to 1.1. And we'll go very quickly through this part. I'm making this video a little too long, but just talking about the standard deviation. There's also standard deviation to each probability distribution, and this is, just plug and play, same type of thing. We're going to use mu here is our expectation. Sometimes you'll see that written as e parenthesis x, the expectation of x, our expected value of the discrete random variable. And this is the formula that we'll use, and once again, just plugging it in, taking the observation x minus the expected value squared times the probability of x, and sum them all up. That would be the standard deviation is the square root of that sum, equal to 7.49 would be